Hello everyone, this is Mike McGinn, your online instructor for NetI 105, and this is the overview for Chapter 8, IP addressing. In Chapter 8, we start to dive into what is really going on with addresses that are assigned at the layer 3 of the OSI model. And we talk about binary and subnet masks and that kind of stuff. And this has got a lot of math in it. I'm going to post some videos that out through the announcements that will hopefully help you grasp some of the detail on this. I'm going to make this overview rather abridged and kind of do my teaching via people that are a lot better at it than I am through YouTube videos and the like. But what I'm going to do is kind of hit some highlights here for your benefit. And so I am sharing my screen right now. Hopefully it'll kick in here. There we go. And what we have here in this picture here on 8.1.1.2, the binary number system. Basically, in a nutshell, IP version 4, which is what we're going to discuss first, you probably have seen it most commonly notated as 4 decimal numbers that are separated by a period. And some terminology here that you need to be aware of is this entire number is what usually we refer to as an IP address. The 4 numbers separated by the dots. Each number between the dots is what we call an octet. And even though it's a little confusing, it's called an octet because it's represented by an 8-bit binary number. Now, if that's confusing to you already, that's probably because you don't know what binary math is or you've forgotten it. I have posted a YouTube video through the announcements on the basics of binary math. It's kind of a cheesy video, but it gets it done. So actually, I thought it was kind of funny, but you may disagree. But at any rate, this binary number 11000000 is the binary representation of 192, and as follows, this number here, the 101010000, represents the number 168. This number here represents the 10, and this number here represents the 10. Notice that those two numbers are identical. So why is that important? Well, it has to do with the subnet mask, which is what separates this number between the unique portion of that number for the host that's on a network and the network portion of the address, which is what's common to all hosts that are on that particular network. For example, the most common subnet mask we see is a /24 or a 255.255.255.0. What that means is that when all these numbers are 1 and you do the binary conversion, it comes to a number 255. So what happens with the mask is that the mask tells the computer what portion of the address is the network address and what portion of the address is the host address. So in the case of a /24, we're moving 24 bits down, and it's saying that to the leftmost 24 bits is the network portion of the address, and the right 8 bits is the host portion of the address. An IPv4 address always has 32 bits. So again, the /24 represents the 24 bits to the left, which leaves 8 to the right. The ones to the left is the network portion of the address. The bits to the right is the host portion of the address. So the way that you would look at this 192.168.10.10 address in the context of a /24 network is that the network is the 192.168.10 network, and this is the .10 host on that network. So there are various video slides here and activities and such that I encourage you to go through that basically gets you through the concept of binary addresses, etc., and converting them to decimal and converting IP addresses to binary format, etc. And the curriculum does test you a lot over this this math because they feel like you got to understand, you need to understand how this all works under the covers in order to really comprehend how IP networks actually work. So in 8.1.2.1 and onward, they talk about the network portion and the host portion of the IP address and the importance of the subnet mask, which I've discussed previously. There are slides that kind of illustrate what I explained here previously. I think once you conceptually understand what they're talking about, you should be able to read this and understand it. One thing I will note to you, there are some special IP4 addresses that represent the broadcast address. And the broadcast address is always the last address in the subnet. So in a /255 network or a /24 network, when all of the host addresses are a 1, or the host binary numbers are 1, then that is, of course, equal to 255, and that means that if that is your destination IP address, it's a broadcast packet. So where it gets a little tricky is when you have something other than a /24 address. Like, for example, you have say a /26 address. Then the decimal notation gets a little confusing. And that's why they really make sure you understand the mechanics of how this all works, because what you need to be able to do is to be able to identify the first host address and the last host address of a given network. So in the case of this example they have here, on a /24 network, first the host address is where the binary number is 7 zeros and a 1, which in converted to decimal is a .1. That is the first in your network. The last host address is going to be where everything is 1s except for the last octet, or the last binary position. Because if the last binary position was a 1, it would be 255, and as I previously explained, a 255 is a broadcast address. So obviously a broadcast address isn't a host address. So where this gets a little tricky is when you have a subnet mask that is different than /24, because then the first and last addresses are going to change, where the last host address may not be 254 and the first host address may not be a 1. So in 8.1.2.5, they talk about bitwise AND operation, and this can be a little confusing, and so I'm going to take you through this a little bit. Basically what it's doing is it's explaining to you how the mask works at a binary level. And in this example, we have an IP4 address here, and what that address here isn't really important. What matters is that this is the binary representations of the 4 octets. And if the subnet mask is a /24, then if you look at a series, if you do the math of just adding these together, what you get based on this translation, where a 1 and a 1 equals a 1, a 0 and a 1 equals a 0, a 0 and a 0 equals a 0, and a 1 and a 0 equals a 0, what you end up with is you end up with 1s in these positions. And then 0s in the other positions. Okay? So that's how the network address is actually calculated. So why is this important? Well, if you have a subnet mask that is different than a /24, say that it was a /22, then the network portion of the address would be the numbers that are converted to decimal up to and through that particular position in the IP address. So it just takes you through here through the rest of the operation there. So at the end result of the example we just saw is that we had a 192.168.10.10 address, a 255.255.255 subnet mask or a /24 mask. When we did the AND operations, we end up with this number here as our network address, which in this case is 192.168.10, and our host portion of the address is, of course, .10. So why all this binary math and IP addresses and network addresses and all that kind of stuff? Why do we even care? Well, if you remember, in the world of the internet and local area networks, we have to know what IP addresses are on our local area network and what addresses are not. And if they're not on our local area network, then we need to send them to the default gateway, which is usually our internet router. So the subnet mask is really what determines whether or not a given IP address is on your local area network or not. It's not the host address, it's the combination of the two. Or I should say the full IP address and the network mask combined to determine whether or not a particular destination is on the local area network or if it needs to be routed out to the default gateway. So how do addresses get assigned to devices? You know, we've got all kinds of devices. We've got PCs, we've got tablets, smartphones, IP phones, network printers, servers, etc. Well, there's two ways that IP addresses get assigned. They can be assigned essentially dynamically through a DHCP server where it, through a protocol called DHCP, the device goes out to a DHCP server and it is given a lease for an address that is available on that local area network. Another way that it can be done is through what is called a static assignment, and that's where you go into the device and manually configure an IP address that is valid for that network. This is an example of where you, in a Windows computer, where you can actually statically assign the IP address. So in this case, we've got an IP address of 10.0.0.1. a /24 mask, and our default gateway is the last host address on the network, which is 10.0.0.254. So that is the IP of our router. Of course, dynamically assigned IP addresses is what's configured by default on Windows computers. That's where, and you've probably seen this before, where it obtains an IP address automatically, and usually it gets its DNS automatically as well. You can statically assign both your IP and your DNS addresses. Remember, DNS is the domain naming server, and that's where IP to host addresses are resolved, and we'll talk more about that later in the course. The IP config command is what you use at a command line that will show you the current IP address, subnet mask, and default gateway on a Windows computer. Should be all familiar with that. So in 8.1.3.3, we talk about the different ways that computers can communicate. And they can communicate in one of three ways. Unicast, which is when a single host communicates with another single host. A broadcast, which is when a single host can send a packet from itself to all hosts on the network. And a multicast, which is the process of sending a packet from one host to a selected group of hosts, possibly even in different networks. These are used for different purposes, but in all three cases, the IP4 address of the originating host is placed in the packet header as the source address. Unicast traffic is pretty much self-explanatory. You know, it's what we're used to working with. Broadcast transmission. This is again where when a single host is sending to all hosts on its network, and it is always the last. It's when the host portion of the IP address is all ones, and DHCP is a protocol that uses broadcasts because when you fire up a computer that has DHCP configured, in other words, it's dynamically getting its IP address from the DHCP server, it has to find the DHCP server first, and it doesn't know where it is. So what it does is it sends out a broadcast to try to find its particular DHCP server. So they talk about directed broadcast and limited broadcasts in here, depending on what you're trying to do. The multicast transmission is where we want to send a series of packets from one source to multiple hosts. Video and audio broadcasts, you know, are all an example of this. Routers will do this to exchange information via routing protocols, distribution of software for remote gaming. There's various things that multicast transmission is used for. Now, IP addresses, IP version 4 addresses themselves, there's two types that you need to be aware of in terms of the full IP address itself. There are public and private IP4 addresses. Public IP addresses are IP addresses that are routable over the internet. In other words, the internet will recognize those. And then there are private IP4 addresses that are only used for local area networks. Private IP addresses, the blocks that they show here, and there's basically a block for each what we call class of network. So those are right here. So in the Class C network, it's the 192.168.0.0 to 192.168.255.255, or 198.68.0.0/16. In the Class B network, which is when you're looking at the second octet of the IP, full IP address, networks in that area are in the 172.16.0.0/12 range, and the Class A networks are in the 10.0.0/8. So depending upon the size of the network that you have, usually you will use the appropriate class private network scheme that you are. So if you're in a very small network, there's a good chance that you'll be in a 192.168.0.0 network, and then large networks that say internet service or very large enterprises might use a 172.16.0.0. Although you can use any of these for any size network, it's all a matter of what you set your mask to. In 192, or I'm sorry, in 8.1.4.4, they get into the legacy classful addresses, and this is where they explain the Class A, the Class B, and the Class C blocks of addresses and why they were created, because there was once upon a time where there was no subnet masks, and that's how those actually came into being. Classless addressing is when we do use the subnet mask, and it's basically referred to as classless interdomain routing, or CIDR. So if you ever hear the word CIDR bannered about, they're really referring to the IP addressing that we use today with the subnet masks employed. There are registries out there that keep track of who's got what public IPs, and some of the major registries are listed here. This isn't tested real heavily on, but you might see a stray question or two on it. So ISPs, or your internet service providers, are responsible for allocating IP addresses. The RIRs are responsible for allocating the IP addresses to the internet service providers, and most companies or organizations obtain their IP4 address blocks from an ISP. So usually an ISP, they'll just give you as many public IPs as you need, no more, no less, because they have a limited number that's allocated to them, and they don't want to waste them. So if you want more than one, you need to tell them how many you want, and usually they're generally accommodating. Sometimes there's a surcharge, but it's generally not too hard to get a block of 8 or 16 or even 32 public IPs if you need them. So if the curriculum doesn't overwhelm you with its explanation of IPv4 and how it's derived and what the significance of the subnet mask is, and host addresses, and first host addresses, last host addresses, broadcast addresses, unicast addresses, multicast addresses, and all those types of things, public IPs, private IPs, et cetera, routable IPs, they throw you right into IPv6 in the same chapter, which I just love. But anyway, that's the way they put together the curriculum. So it would seem to me like you would want to take IPv4 front to back, and then go into IPv6 front to back in a separate chapter. But what they do is they take you into the basics of 4 and the basics of 6 in one chapter, and then they take you into some advanced concepts of 4 and 6 in chapter 9. So why do we need IP version 6? I think I talked about this earlier in the semester. Bottom line is that there was a big concern that we were going to run out of IPv4 addresses, and so they came up with IPv6. IPv6 has a larger 128-bit address space as opposed to 32-bit address space that IP version 4 has. So that's how they came up with that. Also, when you have end-to-end applications that run through the internet, the fact that IPv4 relies on NAT to translate local area or private IP addresses to public IP addresses, IPv6 addresses that issue because now you can have public IPs, as many public IPs as you want. So we now live in a world where IPv4 and IPv6 are coexisting. And one of the ways that they coexist is dual stack. And by default, your Windows computers these days have both IPv4 and IPv6 IP stacks configured on the computer to dynamically obtain IP addresses if need be. So if you do an IP config on a computer that new computer out of the box, you'll see that there's IPv4 and IPv6 addresses assigned to the NIC. Tunneling is when you have an IPv6 only network on local area networks, say on two ends of a VPN or something like that, or even a closed IP network, but the network in between is an IP4 only network. Then the concept of tunneling is employed where actually the IPv6 packets are encapsulated inside IPv4 packets, and once they reach their destination, they're decapsulated and handed off to the destination IPv6 only network. And translation is when you have a router that translates IPv6 addresses into IPv4 addresses and vice versa. So knowing the difference between dual stack tunneling and translation is something that you do need to know. So representing IPv6 addressing in the IPv4 world, we just needed to know binary representation and decimal representation. Well, now that we have IPv6, we also need to understand hexadecimal representation because IPv6 addresses are noted in hexadecimal notation. And that's basically for the purposes of keeping the numbers small. So for example, a hexadecimal numbers go from 0 through 9 and then A through F, which convert to decimal equivalents of 1 through 15. So you can see this keeps it from, becoming, if we did decimals, we would run out of places in representation because you go into two decimals farther down. But and these are the binary numbers that are involved in that. So carried further, if you look at the two character representations of hexadecimal numbers, you can see these are the decimal equivalents and the binary equivalents of those numbers. So this is an example of the format of an IP6 address. You have 8 well, they call them octets in IPv4, and it's escaping me what they call them in IPv6. They are, I don't see it here. It's called a hextet. Well, imagine that. It's right there on the top of the screen, and I didn't even see it. So yeah, we've got hextets in IPv6. So that's what each one of these are. And these hextets can be each of these hextets can be converted into a 16-bit binary number. So that's why, if you can imagine, if we had to convert that to binary, that would be a very, very long binary number. So it's noted in hextet. So that's the format of a IPv6 address. So some preferred format examples. Here's some different IPv6 addresses just listed in a list here. Now in terms of noting IPv6, there's some interesting rules. Rule number one is you can get rid of leading zeros when you note it. So if the address is this, you can note it as that. Rule number one. Okay, so you're just getting rid of the leading zeros just to make the IP address shorter. Rule number two is that you can get rid of any hextets of all zeros by just having a double colon. So in this example, we have a double colon right here that eliminates all the zeros that are piled up right here. Okay. Now, there's a catch. You can only do that once. You can't have multiple double colons in an address or it'll be invalid. Ergo, that's why you don't see a double colon up here between the 1111 and the 0db8. You've got db8 colon 0 colon 111 colon 200. So obviously it makes sense to do the double colon where you've got all of these slew of zeros here because it makes the notation a lot smaller. So you've got some activities to help you practice that so that you can figure out how to use that, and lots of fun stuff. So like IPv4, we have unicast addresses, which are, you know, individual addresses of individual hosts and the one-to-one communication between the two. We also have multicast addresses used for a single host to send IPv6 packets to multiple destinations. And then an Anycast address is an IPv6 unicast address that can be assigned to multiple devices. Kind of sounds like a broadcast address, doesn't it? A packet set to an Anycast address is routed to the nearest device having that address. Anycast addresses are beyond the scope of this course, which means we don't need to worry too much about that, do we? So unlike IPv4, IPv6 does not have a broadcast address. However, there is an IPv6 all nodes multicast address that essentially gives the same results. Also recall in IP version 4 we discussed with the subnet mask, we had the ability to basically split the IP address into a network portion and a host portion. Same is true for an IPv6 address. The default prefix or the default mask of an IPv6 address is /64, which basically takes the address and splits it right down the middle. So as you can imagine, with a /64, you can have a whole lot of networks and a whole lot of hosts. So lots of room for anything you can conceivably want to do. So within the IPv6 unicast address, there are different types. Yes, it even gets down to a different level of complexity. There is the global unicast address, and the global unicast address is similar to a public IPv4 address. These are global unique. In other words, no two are the same. And they're all internet routable. So they can be assigned statically or dynamically on a device, and there are some important differences on how a device receives IPv6 addresses dynamically compared to DHCP for IP version 4, which we'll get to. The link local addresses are used to communicate with other devices on the same local link. In other words, the same local area network. With IPv6, the term link refers to a subnet. Link local addresses are confined to a single link. Their uniqueness must only be confirmed on that link because they are not routable beyond the link. In other words, routers will not forward packets with a link local source or destination address. Kind of sounds like private IP4 addresses, doesn't it? Then there's a loopback address, which is always a host address of or an IP6 address of :1/128, and an unspecified address is when an all zeros address represented in the compressed format as ::/128. So the loopback address is obviously a testing address, and an unspecified address is just one that is not is used as a source address when the device does not yet have a permanent IPv6 address or when the source of the packet is relevant to the destination. So, and then there is unique local addresses, and unique local addresses are kind of like private addresses for IPv4, but there's different as well. Unique local addresses are used for local addressing within a site or between a limited number of sites. These addresses should not be routable on the global IPv6. Unique local addresses are in the range of FC00::7 to FTF::7. And then IP4 embedded is these addresses are used to help transition from IP4 to IPv6, and IP4 embedded addresses are beyond the scope of this course, which means we don't need to worry about it right now. So link local addresses usually start with an FE80. Remember, these are not global routable addresses. And so, as you can see here, they won't go past the router, and but they can all see each other. And the FE80, that's the first 10 bits of the address, and then the remaining 54 bits of the network portion of the address are all zeros, and the interface ID is of course the host address. So in 8.3.1 we talk about ICMP and look at the differences and similarities between ICMP on IP version 4 and ICMP on IP version 6. ICMP protocol is used in both ICMP 4 and 6 for host confirmation, in other words like a ping command. You determine whether a destination or service is unreachable, time exceeded, route redirection, etc. With host confirmation, the DIMCP echo command echo message is used to determine if a host is operational. Destination service unreachable is another message. Time exceeded, the time to live, and the route redirection is to tell it that there's a better route available. These are all common protocol messages in both 4 and 6. In IP version 6, there is some extra there is an extra protocol. One is the Neighbor Discovery Protocol, or NDP, and what it does is ICMP messaging can actually find a router, a IPv6 router on your network, and these are the messages that are associated to that. Where that comes into play is when it needs to obtain a global unique address or local link address. It can use basically the IPv6 version of DHCP, and one such is stateless address auto configuration, or SLAC, and it will send an RS message to the router, and the RS message is sent as an IPv6 all routers multicast message. So basically a IPv6 host will send this message out to say, hey, is there a a SLAC router out there, and if so, then the router sends an RA message, which includes the addressing information to the host, very similar to DHCP. There's also DHCP version 6, which we will get into in a little bit. ICMP version 6 Neighbor Discovery Protocol includes a couple more messages. The neighbor solicitation, neighbor advertisement messages are used for net address resolution and duplicate address detection. So address resolution is to basically determine the MAC address of the destination host that it's looking for, kind of like an ARP message, and so that's what that is used for, and also to determine if there's already an IP address out there with the same as what you want to use or what's been assigned to you. 8.3.2 gets into testing and verification. It shows you the ping command in IP version 4. So you can testing connectivity to the local LAN. You can do a ping command to say, hey, are you there? And it'll reply back. Trace route is where you actually will trace the path from host to destination, and it'll show you the hops it goes through to get there. Most of these you probably have used or are somewhat familiar yet with. There's a nice packet tracer on learning how to use these commands for both IPv4 and IP version 6 and 8.3.2.5. And there are some good labs and packet tracers in this chapter, and this is one of those chapters that I don't assign everything that's in the chapter to you as far as packet tracers and labs, but I tell you, if you don't already have this down pat, this is a good chapter to do everything you can do in it, and do it twice, because it'll pay dividends down the road, not only later in this course, but probably for the rest of your life. So that's your overview of Chapter 8. Lots of deep stuff in here, lots of binary, hexadecimal, decimal, subnet masks, IP version 4 and IP version 6, differences in similarities, I'm sorry, getting to the end of the talk, of the two versions. So lots of meat in this chapter, and so give it a really good hard read. We kind of have a little reprieve in the coursework between now and when your next set of assignments are done. That's on purpose because there is a lot of material here that you need to go through, and I can't discount this, or I can't emphasize this enough. The next two chapters in this course are the ones you're going to need to know the most if you plan on a career in infrastructure. The rest you can Google, but if you don't understand how this stuff works, you're not going to be able to troubleshoot yourself out of a web paper sack. So I guess that's my sermon for today. You guys have a good week, and I will be coming out with Chapter 9 very soon. Have a good one.